Hi, in this video, we are going to continue our problem solving series on complex numbers and polynomials. So we start off with this question. It says P of x is equal to 1 plus x squared till x power 17 whole square minus x power 17. And P of x has 34 complex roots of the form z of k is equal to rk cos of 2 pi alpha k plus I sine of 2 pi alpha k, where k goes from 1 to 34. And we have 0 is less than alpha is less than equal to alpha 2, so on till less than equal to alpha 34 is less than 1. So this information is also given. We have to find out the first 5 alphas. Find out alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 plus alpha 5. So basically the first 5 roots and the arguments of those roots we have to find out, and that will give us the sum. Right? Now, if you look at the polynomial, this is a 34-degree polynomial because x power 17 is squared. So that's why it has 34 roots. And we can see easily that we can rewrite this polynomial using the GP formula. This is a geometric progression, so I can write it as x power 18 minus 1 by x minus 1 whole squared minus x power 17. And if you simplify this, this becomes x power 18 minus 1 whole squared minus x power 17 x minus 1 whole squared divided by x minus 1 whole squared. And after a little bit of simplification, expand it and simplify this, you'll get x power 36 minus x power 19 minus x power 17 plus 1 divided by x minus 1 whole square. And basically this can be factorized. So what we get is p of x becomes x power 19 minus 1 multiplied by x power 17 minus 1 divided by x minus 1 whole square. That is my p of x. Now, what you can see here from this expression of p of x, we can realize that p of 1 is not equal to 0. P of 1, if you think about it, would be basically 18 square minus 1. Because every time you put x is equal to 1, there are 18 terms here. So 18 square minus 1 is p of 1, which is not equal to 0. And p of x can also be written like this. So therefore, we can rewrite it as x minus 1 whole square p of x is equal to x power 19 minus 1 and x power 17 minus 1. Now, our job is to find the 34 roots of this. 34 roots of p of x. Right? Now, what happens here is that we can say that there are 19 roots of this expression, 19 roots, and there are 17 roots of this expression. So that those add up to 36 roots. But if you exclude 1 here and 1 here, 1 is a root of both the equations. So x power 19 is equal to 1 and x power 17 is equal to 1. 1 is a root for both the equations. So if you remove 1 from here, you get 18 roots here and 16 roots here. So total 34 roots which are other than 1. Other than 1, right? Those roots will be also roots of p of x, because whenever the factors on the right hand side become 0, p of x will become 0. So how do I write the roots of this other than 1? X power 19 is equal to 1 has roots. X is equal to cos of 2k pi by 19 plus I sine 2k pi by 19, where k goes from 0 to 18. However, you have to exclude the zero root, right? So if you exclude the zero root, k starts from 1 to 18, right? So your root will be basically cos of 2 pi by 19 plus I sine 2 pi by 19. And then the next one would be cos of 4 pi by 19 plus I sine 4 pi by 19. And so on. It will go on to cos of 18, it will be 36 pi by 19 plus I sine of 36 pi by 19. These are the 18 roots that you get from here. All of these are complex numbers, and these are the first 18 roots. And here, when you do x bar 17 is equal to 1, you get roots of cos of 2 pi by 17 plus I sine of 2 pi by 17, and so on. The next one will be cos of 4 pi by 17, and the last one would be cos of 16 into 2 pi. So 32 pi by 17 plus I sine 32 pi by 17. These are the 16 roots from here and the 18 roots from here, which make up the 34 roots. We have to find out the smallest 5 values of alpha. Right? If you notice, the way the alpha was written was rk cos of 2 pi alpha k plus I sine of 2 pi alpha k. So alpha k is this angle divided by 2 pi. So alpha 1 would be 2 pi by 19 divided by 2 pi, which is 1 by 19. And alpha 2, the next smallest one will be 1 by 17 from here, 1 by 17. Alpha 3 would be 2 by 19. Alpha 4 would be 2 by 17 from 4 pi by 17 here. Finally, alpha 5 would be 3 by 19. So what we have to do is add up all of this, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 plus alpha 5, right? And the answer basically will come out to be alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 plus alpha 5 will come out to be 159 by 323. You can check this, sum it up, and check whether this is happening for you or not. Okay? So that is the solution of the first question. It was a simple question where we have to basically find out how the roots of the overall polynomial will come. Okay. Okay. The next problem that we will look at is this one. I will write the question here. Let Z1, Z2 till Z power 2016 not equal to 1 be the non-trivial roots of the equation x power 2017 equal to 1. We have to find the value of, find summation k goes from 1 to 2016, 1 by 1 plus z of k. These are the complex roots, the non-trivial roots of the equation, this one. We have to find the sum of 1 by 1 plus zk for all of those non-real roots, right? Now, you have to realize that 1 is a root of x power 2017, and the total number of roots must be 2017, and 1 is one of the roots. The other roots will be there 2016 other roots of x power 2017 equals 1. And notice that this polynomial x power 2017 minus 1 equal to 0 has real coefficients. So if zk is a root, then zk conjugate is also a root, right? Zk and zk conjugates are both roots of this polynomial. Also, we know that if zk is a root, zk power 2017 is equal to 1. Taking modulus on both sides, we get mod of zk power 2017 is 1, which implies mod of zk is 1. And if mod of zk is equal to 1, then mod of zk square is equal to zk conjugate, which implies 1 is equal to zk into zk conjugate, and therefore zk conjugate is 1 by zk, right? So what we know is that the equation x power 2017 equal to 1 has roots 1 and complex numbers zk and 1 by zk, and many other complex numbers like this. They will always come in pairs like this, right? Okay. So now think about how you want to add up k is equal to 1 to 2716, 1 by 1 plus zk. So technically what do I have to do? I have to do 1 by 1 plus z1 plus 1 by 1 plus z2 and so on till all the roots are covered 1 by 1 plus z power 2016, right? However, we know that if z1 is a root, z1 is a root, then there will be some other root somewhere here which will be 1 by z1. So some power zr, zr some root is basically z1 conjugate or 1 by z1, right? And the roots come in pairs. So instead of having 2016 terms in this summation, what I can always do is do it in pairs like this, 1008, and you have a pair of 1 by zk plus 1 by 1 plus zk conjugate. And grouping one term like this and one term with the conjugate of z1, right? Because I'm guaranteed that since there are even number of roots like this, complex roots, they are all going to be conjugates of each other and will come in pairs. So I'm going to not do the summation from 1 to 2060, rather I will do it from 1 to 1008 using this 1 by 1 plus zk and 1 by 1 plus zk conjugate. Now utilizing the fact that 1 by 1 plus zk and 1 by 1 plus zk conjugate can be written as 1 by zk, and summing it up from k is 1 to 1008, you will realize that this becomes 1 plus zk by 1 plus zk summation k 1 to 1008, which is clearly 1008. So the question is solved immediately as soon as you realize that all the roots are going to come in pairs and zk conjugate is equal to 1 by zk. When you group the terms like that together, the summation of 1 by 1 plus zk plus 1 by 1 plus zk conjugate becomes simply 1, and therefore the answer will be 1008 in this case, right? Let's look at the next problem, question number 3. Here we have, let z be a complex number, let z a complex number such that z power 23 is equal to 1. We have to find the value of summation k goes from 0 to 22 1 by z to the power 2k plus z power k plus 1. Now this is a very important question because such things can come in your exam, and we will use an idea that is very general and quite useful. So z power 23 minus 1 is equal to, we can factorize it like this, z power 22 plus z power 21 plus z plus 1. And since this is equal to 0, therefore, if you are talking about complex roots, z is not equal to 1. 1 is not a complex number. 1 is a real number. So we have, for all the complex roots, we can say 1 plus z square till z power 22 is equal to 0. Or basically you can say z power 22 plus z power 21 plus z power 20 plus z cube plus z square plus z is equal to minus 1. So this result is satisfied by all the complex roots of this equation, right? Now think about it. if k is not a multiple, if k is not a multiple of 23, not a multiple of 23, then z power k also satisfies the equation z power k power 23 equals 1, because, or basically what I'm saying is, if you replace z with z power k in this equation, you'll realize z power k power 23 is z power 23 power k equals 1 power k equals 1. So as long as k is not a multiple of 23, what we have is, if z satisfies this equation, z power k also satisfies this equation, right? So from this equation we had deduced this. So we can also say that instead of z, if I put z power k here, z power k plus z power 2k plus z power 3k, so on till z power 22k, that will also be equal to minus 1, right? If you are not convinced by this, let's take some examples and understand what is going on. So instead of z power 23, let's take the example of z power 3 equals 1, right? Now, we know that the roots of this equation are 1 omega omega square and 1 plus omega square. Sum of the roots is equal to 0, and therefore omega plus omega square is equal to minus 1. So these are the two non-real roots of this equation. They are adding up to minus 1. Just like when we had z power 23 is equal to 1, we had z plus z square plus z power 22 was adding up to minus 1, right? Now, what I want to say is, let's say k is 2. What I will say is, if you do omega square plus omega square square, that should also add up to minus 1, just like this. So what you get is omega square plus omega power 4 is equal to omega square plus omega cube times omega, which is 1. So omega square plus omega, which is minus 1. So if z and z square are roots of this equation, we had z plus z square equals minus 1. I'm going to say that z square plus z power 4 is also minus 1. If k is equal to 4, for example, I'm going to make the claim that z power 4 plus z power 4 square is also going to be minus 1. You can check that z power 4 plus z power 8 is same as z plus z square is equal to minus 1, right? So as long as k is not a multiple of 3, if k was a multiple of 3, for example, k is 6, then what is z power 6 plus z power 12? Notice that in this case, since z power 3 is 1, this is 1 and this is 1, it is equal to 2 and not minus 1. So the only case this property doesn't work is when k is a multiple of n. So in the case of our problem, if z power 23 is equal to 1 and the non-real roots are z, z squared, z cube till z power 22, we know that z plus z square plus z cube plus z power 22 is equal to minus 1. We have just now seen examples. We have seen that z power k plus z power k power 2. So z power 2k plus z power 3k plus z power 22k is also minus 1 as long as k is not a multiple of 23. If k is a multiple of 23, then obviously all the terms here will become 1 and it will not be adding up to minus 1. So Remember this property. This property is super important. You might encounter problems later, which will again use this idea. So now that we know this result, we will be using this result to prove or find out the summation that we need. So let's look at that summation. The summation was sum of k goes from 0 to 23, 1 by z power 2k plus z power k plus 1. Now, this can be written as, if you put k is equal to 0, you will get 1 by z power 0 plus z power 0 plus 1 plus summation from k is equal to 1 to 22. This will become z power 2k plus z power k plus 1. So I'm getting 1 by 3 here. All of these are 1, 1 and 1. 1 by 3 plus summation from 1 to 22. 1 by z power 2k plus z power k plus 1. Now we try to simplify this new summation k from 1 to 22. Now by the GP formula, this can be easily written as 1 by 3 plus summation k goes from 1 to 22. This becomes z power 3k minus 1 in the denominator, z power k minus 1 in the numerator, right? And we know that z power k is the same as z power 24 power k. Why? Because z power 24 is equal to z, since z power 23 is equal to 1. So this top part we can write as 1 by 3 plus summation k goes from 1 to 22 z power 24k minus 1 divided by z power 3k minus 1. Right? Because z power 24k is the same as z power 3 z power k minus 1. Now if you try to calculate this or divide this expression, you should get 1 by 3 plus summation k goes from 1 to 22. Let's divide this expression. This expression would give us simply z power 3k. Like this is like saying what? Z power 3k, let's take it as x. We have x power 8 minus 1 by x minus 1, right? So you'll get x power 7, x power 7 plus x power 6 plus x plus 1. X power 0 finally. This will be the value here. So this is what? This is z power 21k plus z power 18k plus z power 15k plus z power 12k plus z power 9k plus z power 6k plus z power 3k plus z power 0k plus 1. Right? And summation is from k goes from 1 to 22. Right. This whole expression. After dividing the numerator by the denominator, this is what I am getting. Right. Now, let's try to think about what we will do here. We already know one standard result, that as long as k is not a multiple of 23, we have z power k plus z power 2k plus z power 22k till that is equal to minus 1. We know this from before. As long as k is not a multiple of 23, right? So when I'm doing the summation here, when you put k is equal to 1, you get z power 21. When you do k is equal to 2, you get z power 42, right? And you are going to go up to k is equal to 22, right? Like this summation I'm trying to do. Like you can do the summation in a vertical line like this. Basically, I can split it like this. K is equal to 1 to 22, z power 21k. plus k is equal to 1 to 22 z power 18k. All of these till k is equal to 1 to 22 z power 3k. All of these will add up to minus 1 because none of these numbers 21, 18, 3, none of these numbers are multiples of 23. The final term will be k is equal to 1 to 22, 1, which is simply 22. So we have 7 terms here, 7 summations here, which are minus 1, minus 1, minus 1. So you get a 22 minus 7 or 15. 15 comes out from here. And we have 15 plus 1 by 3. So basically the answer becomes 46 by 3. That is the final summation. If you are confused about something, go back to the beginning of the problem, see what we have proved earlier, and you should realize that this is making sense. Let's move on to the next question. Question number 4 talks about if R1, R2, R2018 are the non-real roots of z to the power 2019 equals 1, then we have to find the value of find R1 plus R2 plus R power 2018 plus 2018 whole divided by 1 plus R1, 1 plus R2, and the product till 1 plus R power 2018. This is a straightforward problem. Like we can say that z power 2019 minus 1 can be written as z minus 1, z power 2018 plus z power 2017 plus z plus 1. This is the factorization. And we know that R1, R2, R2018 are the non-real roots. So obviously the roots are non-real roots, so they will be factors of this expression. So we can say z power 2018 plus z power 2017 till z plus 1 can be written as z minus R1, z minus R2 till z minus R2018. This is a 2018 degree polynomial and we have 2018 roots. Those are roots of this polynomial. The other root is simply 1, right? So we can definitely write it as a product of factors like this, right? Now, we also know by Vieta's formulas, if R1, R2 till R2018 are roots of Z power 2018 plus Z power 2017 plus Z plus 1. Therefore, the sum of all the roots R1 plus R2 till R2018 would be equal to minus 1 by 1. By Vieta's relation, this is minus 1. So this is minus 1. So notice that the top part here is minus 1 plus 2018 is 2017 by whatever is the denominator. So all we have to do is figure out this denominator. And in order to get the denominator, what you should do is put z is equal to minus 1 in this expression. So if you do that, there are 2018 terms. So you get factors like this, minus 1 minus R1, minus 1 minus R2, till minus 1 minus R2018. And you can take minus 1 common in all of them. And since the powers are 2018 terms are there, so it will become simply plus 1. You'll get the product of 1 plus R1, 1 plus R2 till 1 plus R2018. And that is basically obtained by putting z is equal to minus 1 in this. When you do that, you will realize that the value of this term will become basically 1. All the terms here from z power 1, z power 2, all of these terms will cancel and 1 will remain. Because the terms will be 1, minus 1, 1, minus 1 alternatively, right? All of these terms cancel, 1 remains. So therefore this product value is equal to simply 1. And if that value is equal to 1, the answer for our overall question is 2070. So it's a direct question using the properties of polynomials. Nothing very difficult here. Let's look at the next problem. Question number 5. Let Px be equal to the polynomial x power 5 minus x squared plus 1. And let Qx be equal to x squared plus 1. Denote the roots of P of x. Denote the roots of P of x by R1, R2, R3, R4, R5. You have to evaluate the product Q of R1 times Q of R2 times Q of R3 times Q of R4 times Q of R5. So technically P of x, which was equal to x power 5 minus x squared plus 1, can be written in terms of the roots like this: x minus R1, x minus R2, x minus R3, x minus R4, and x minus R5. And if you think about it, what is Q of R1? Q of R1 times Q of R2 times Q of R3 times Q of R4 times Q of R5 is basically the product of j goes from 1 to 5. It is Rj plus I, and product of j goes from 1 to 5. It is Rj minus I. Why? Because it is basically Rj square plus 1. Rj square plus 1 can be split as Rj square minus I square and split as Rj minus I times Rj plus I. So if you think about it, if I think of P of I is actually I minus R1, I minus R2 till I minus R5. So that is clearly the value that you get when you do Rj minus I 5 times, right? R1 minus I, R2 minus I, that is the same thing. So this is P of minus I, and this is P of I, and this is P of minus I. Both will give us a negative sign, and negative negative will become positive. So you can quickly see that P of minus I will be minus 1 power 5 I plus R1, I plus R2 till I plus R5. And this was what? This was minus 1 power 5 R1 minus I, R2 minus I till R5 minus I. So finally you are getting P of minus I times P of I is equal to this product, right? And that means that it is equal to mod of P of I whole square. We have seen this property before. P of a complex number, P of Z times P of Z conjugate is equal to mod of P of Z whole square, right? And here you have P of I and P of minus I, which are conjugates of each other. So it is mod of P of I whole square. And what is P of I? P of I is basically I power 5 minus I square plus 1. And I power 5 is simply I, and minus I square is plus 1, so I plus 2. So this is 2 plus I mod whole square, and mod of 2 plus I is root 5, so answer is 5. So the product of Q of R1, Q of R2 till Q of R5 is simply equal to 5, and that again comes by the properties of complex numbers. We'll look at one final question, question number 6. And this question will employ some inequalities that you may have seen before. If you haven't, you should check out some of my videos on inequalities that are present on the channel. So let's look at the problem first. X power 4 plus 3x cube plus ax square plus bx plus c be a polynomial with real coefficients, which has four real roots in the interval -1 to 1. In the interval -1 to 1. We have to prove that 1 minus a plus c whole square plus 3 minus b whole square is greater than or equal to 5 by 4 power 8. So right now doesn't make any sense. How are we getting this expression 1 minus a plus c whole square and 3 minus b whole square? Doesn't make much sense. Doesn't seem to be very directly related to the problem. But if you think about it for a little bit, you will realize what is happening. So your p of x is x power 4 plus 3x cubed plus ax square plus bx plus c. And we say that let x1, x2, x3, x4 be the real roots, of p of x in the interval -1 to 1, right? If these are the real roots of p of x in the interval -1 to 1, they have already said that in the problem that it has four real roots in this interval. We are saying x1, x2, x3, x4 are the four roots. So think about it. What is p of I? P of I is basically 1 plus 3i cube plus ai square plus bi plus c. So that is equal to 1 minus 3i minus a plus bi plus c. And that can be written as 1 minus a plus c plus b minus 3 times I. Right? This is p of I, right? Now notice that as soon as you did p of I, you are getting terms like 1 minus a plus c and b minus 3. So what we have to prove here is having those terms itself, right? So if you look closely, you will realize that the LHS here is simply mod of p of I whole square. That is going to be 1 minus a plus c whole square plus 3 minus b whole square, right? The modulus of p of I whole square of that is basically this, right? Now, mod of p of I whole square can be written as p of I times p of minus I, right? So we can write that like this, and we know that this is equal to 1 minus a plus c whole square plus 3 minus b whole square. And if you think of p of I would be x1, x2, x3, x4 were the roots. So it will be I minus x1, I minus x2, I minus x3, I minus x4. And p of minus I would be minus I minus x1, minus I minus x2, minus I minus x3, minus I minus x4. So you can take minus common from each of these terms, and this is I plus x1 and this is I minus x1. So the product of p of I times p of minus I is equal to I plus x1 into I minus x1. So it is I square minus x1 square, I square minus x2 square, and similarly I square minus x4 square. And I square is -1. So -1 minus x1 square, this is -1 minus x2 square, -1 minus x3 square, and finally -1 minus x4 square. So what we are getting is p of I times p of minus I is equal to the product of 1 plus x1 square, 1 plus x2 square, 1 plus x3 square, and 1 plus x4 square, right? So since both the expressions are same, this is equal to 1 plus x1 square, 1 plus x2 square, 1 plus x3 square, 1 plus x4 square. But our job was to show that this quantity is greater than equal to 5 by 4 power 8. That was what I wanted to prove, right? So technically now our job is to show that we need to show that 1 plus x1 square, 1 plus x2 square, 1 plus x3 square, and 1 plus x4 square is greater than equal to 5 by 4 power 8, where x1, x2, x3, x4 lie in interval -1 to 1. So this is what we boils down to. This is what we have to prove. Now, this is where we'll use some inequalities, some basic inequalities. So what I will say is I will take log here and I need to prove that take log on both sides. You have ln 1 plus x1 square plus ln 1 plus x2 square plus ln 1 plus x3 square plus ln 1 plus x4 square is greater than equal to 8 times ln 5 by 4. This is what I want to show now, right? So in order to analyze this, we will prove it by concavity and convexity of functions. Use the function g of x is equal to ln of 1 plus x square. Now this function is basically going to be concave up in the interval. In the interval -1 to 1, it is concave up. How do I know that? Concavity or convexity can be decided by the double derivative of the function. If I take g dash x, I'll get 1 by 1 plus x squared times 2x. That is twice of x by 1 plus x squared. And if you take g double dash x, you get twice of derivative of x is 1. So 1 into 1 plus x squared minus x into 2x divided by 1 plus x squared whole square. So this is becoming simply 1 minus x squared by 1 plus x squared whole square. And since x lies between -1 to 1, 1 minus x squared is positive. 1 minus x squared is positive and the denominator is positive. So what we are getting is g double dash x is greater than 0. So it's a concave up type of curve. If my function was g of x is equal to 1 plus ln of 1 plus x squared, then the function graph has to be concave up in the interval -1 to 1. Concave up graph looks like this. And now we will use Jensen's inequality, which says that the sum of a goes from 1 to 4 ln 1 plus x k square whole divided by 4 will be greater than equal to ln 1 plus summation of k goes from 1 to 4 xk by 4, and this term is squared. So basically, if you take three terms, this is x1 ln 1 plus x1 square, x2 ln 1 plus x2 square, x3 ln 1 plus x3 square. You connect it like this, you can easily see that the centroid of the triangle is above. Centroid of the triangle is above the actual value of the function, which is at the average of the three x's. The value of the function here would be summation of ln of 1 plus summation of xk, k goes from 1 to 3 xk square by 3, right? I'm making a mistake here. I will just draw this on concave up function nicely. Take any 3 points. This is my triangle. This is x coordinate is x1, x2, x3. So the centroid of this triangle will be x1, plus x2 plus x3 by 3 and f of x1 plus f of x2 plus f of x3 by 3. And you should notice that the centroid of the triangle is at this point, the y coordinate of which is bigger than the y coordinate at this location. We are saying that f of x1 plus f of x2 plus f of x3 by 3 is clearly greater than equal to f of x1 plus x2 plus x3 by 3, which would have been 1 plus ln, no, ln of 1 plus, instead of x square, I have x1 plus x2 plus x3 by 3 square. So this inequality is Jensen's inequality for 3 variables. We are employing Jensen's inequality for 4 variables here. So we are saying summation k goes from 1 to 4 ln of 1 plus xk square whole divided by 4 is greater than equal to ln of 1 plus summation k goes from 1 to 4 xk divided by 4 whole square. And now looking at the fact that x1, x2, x3, x4 are roots of the polynomial. The polynomial was given by x power 4 plus 3x cubed plus ax square plus bx plus c. We already know that summation of k goes from 1 to 4 is equal to minus 3. This is by Vieta's relation, right? So this part is basically minus 3. So you get this is equal to ln 1 plus 9 by 16, because it is minus 3 by 4 whole square. So that is 9 by 16. So this is coming as ln of 25 by 16. And what we are getting is summation k goes from 1 to 4 ln of 1 plus xk whole square is greater than equal to 4 times ln 25 by 16. And that becomes equal to 5 by 4 square. So you can write it as this is equal to 8 times ln 5 by 4, which is equal to ln of 5 by 4 power 8, and which implies that ln of 1 plus summation here, summation of k goes from 1 to 4 ln of 1 plus x square is greater than equal to this. Now that means that you can write it as a single product of 1 plus xk whole square and so on, x1 whole square, 1 plus x2 whole square. Instead of summation of 4 logs, you can write it as 1 log is greater than log of this. So that implies that product of 1 plus x1 square, 1 plus x2 square, 1 plus x4 3 square and 1 plus x4 square is greater than equal to 5 by 4 power 8. Once you remove the logs, this is proved. And if you recall, this was equal to p of minus I into p of I, which was mod of pi whole square, and mod of pi whole square was equal to the LHS. So the overall inequality is proved. Again, the concepts that we have used in this solution are these ideas: p of I times p of minus I is equal to mod of pi whole square. We wrote p of x as x minus x1, x minus x2, x minus x3, and x minus x4. And then calculating p of I and p of I minus I product is pretty straightforward. And then we took log and we used Jensen's inequality for a concave up function. Jensen's inequality with 4 terms for a concave up function. So I explained using the graph how for three terms the Jensen's inequality is valid. We are just extending it, and inequality is valid in general for n terms also. So that concludes the proof of this problem. Hopefully you have learned something from this video. The questions here are useful for your roots of polynomials type of questions that you might find in JEE Advanced, and also as if they are part of our polynomials course. In the next few videos, we will make more content about it. So stay tuned. If you like the content, please subscribe to the channel, share the videos with your friends. Your support makes the channel grow and helps me get you more content like this. See you next time.